السلام عليكم ورحمة الله وبركاته. Are you able to hear my voice? Okay. And are you able to see the screen? Is it visible for you? Okay. So we are going to start. Our class directly. In the last classes, we have talked about the different types of foundation. We have taken into account the isolated foundation. We have learned how to deal with rectangular foundation, how to deal with a square foundation. We have learned how to do one-way and two-way shape. And lastly, we have taken the bending moment of a combined foundation. Okay. And I have showed you how would you get the reinforcement in terms of a combined foundation. Okay. Now today's session is going to be about the new topic, which is design of columns. Since we have a limited time only, and you need to know about the columns. Okay. So what I have done already. I think I have uploaded for you the slides. If they are not uploaded, then I'll upload them now. Okay, or after the session. They are available in the PowerPoint. Nevertheless, I have shifted them to the whiteboard so I can send for you one picture, like whatever I have done in case of a combined footing, where you can have it rather than writing yourself once again. Okay. So if you see here, I have like multi slides. We're going to go slide by slide, and we're going to learn the different things here. Okay. Now the first thing that we need to know is the difference between a column and a wall. Okay, the difference between a column and a wall. Now according to the BS code, says for you, if we are talking about a two-dimension element, which is vertical element, of course, because column and wall, both of them are vertical. If we are talking about a vertical element, in the cross section we are going to have a smaller dimension, and we are having the longer dimension. So let us say the depth and the width. Okay, so we have a depth and we have the width. Now the code says for you, the BS code says for you, if your depth is more than 4 times if your depth is more than 4 times of your width, then this element is considered as a wall. Okay. So for example, if we have a column, or we have an element, if we have an element which is 900 into 200, then this is not going to be as a column, but this is going to be as a wall. Why? Because once again, the longer dimension is more than 4 times of the shorter direction. So this is considered as a wall. Now if we have case number 2, where we are talking about, for example, 200 into 700. Now anything lesser than 4 times of the shorter dimension, my shorter dimension is 200. Anything lesser than 4 times or equal to 4 times is going to be considered as a column. Now is it clear for you when to classify this vertical element as a column, and when to classify it as a wall? Okay. Now that's regarding the wall and the columns. Any question you have here? Any question you have for the columns and the wall, or is it clear already? So if I have brought for you in the examination 2 vertical members with the cross section, you should be able to figure out which one is a column and which one is a wall. Okay. Now going for the second slide, which is talking about load applied on the column. Okay, load supplied on the column. So this is slide number 1. Let us say this is slide number 2. Okay, load supplied on the columns. So let us take this particular example. Here they have given us that we have 2 columns. Okay, or let us say 4 columns. So this is C1, this is C2, this is C3, and this is C4. And we have B1 here, B2, let us say B3 here, and then B4 here. Now if we are talking about C1, C1 is going to take the loads from which elements exactly? C1 is going to take the loads from which beams? C1 is going to take the loads from B1 and from B2 as well. Okay, so it will take from B1 and B2. How much is the load going to be taken from both of these things, or both of these beams? So we have this is my beam, there is a column here. Okay, so this is my B1, this is my C2, and this is my C1. Now half of the loading, whatever loading is there, okay, half of the loading here is going to go here if it's a simply supported, okay, which is going to be representing the reaction of beam number 1. Okay, beam number 1 is going to have 2 reactions, one on the left side, one on the right side. Okay, so this is representing the reaction of beam number 1. Similarly, when we talk about the other beam, if we talk about the other beam, this beam, which is beam number 2, it is supported by C1 and C3. And we can see, okay, we can see that half of the loading is going to go for this column or this support, and then the other half is going to go to the other support. So I can say as well, C number 1 is taking the reaction. Okay, it is taking the reaction of beam 2. Okay, so the first load is going to be B1, reaction of B1. Second is going to be reaction of B2. Okay, why this is happening like this? Okay. Okay. So the reaction of beam number 1 and the reaction of beam number 2, which are represented here. So this is the reaction of beam number 1. This is the reaction of beam number 2. Plus there is an additional force, which is going to be the self weight or own weight of the column, which is given as, what did we say regarding the self weight of the column? How it's going to be calculated? How it's going to be calculated? The self weight of the column. We said it is going to be 24 into B into depth into height of the column, or L. Okay. So if the dimensions are given, you will go and calculate it based on this equation. If the dimensions are not given yet, you need to estimate the column estimated as 10% of the load. Okay. So once again, we have the column to take all the reactions from the different beams. If you are having 2 beams, means you will have 2 reactions plus the self weight. Okay, that's going to be the value of your N on the column. Okay. Now once again, how to calculate the self weight? The self weight will be calculated as 24 into the unknowns, which are B, D into L. If they have not been given, then you can calculate it as 10% of the load. Okay. So if the dimensions have been given, self-weight is going to be a clear value of 24 into width into depth into L or height. Okay. If it's not given, then you need to estimate it as 10% of whatever load. And this is clearly have been written here that the self-weight can be calculated from unit weight, which is 24, multiplied by volume of the concrete, which is area into height. Area is B into D. Height is L for the column. If the dimensions have not been given, then the self-weight can be estimated by 10% of the loads from the beams. Okay, so depending on how many beams are there, you will have the loading on the column. So for example, if we are going to take this particular structure, okay, if we are taking this particular structure, this column is taking how many loads? This particular column is connected to how many beams? Okay. Okay. You will see that this particular column is connected to 3 beams. So beam number 1, beam number 2, and beam number 3. So this particular column is going to take the reaction of beam number 1, beam number 2, beam number 3, and its own self-weight. Okay. Here, for example, it's going to take 2 beams only, since 2 beams are connected or attached to the column itself. Okay. Are we clear about the concept of getting the loading for the column? Are we fine with it? Okay. There is another method. Which is cutting the loads of the slab into areas. Okay, and then you can divide it to the columns. But I wouldn't go and explain it for you. Okay, it's better to use the reaction as it's the most accurate method. Okay. So once again, by now we have learned 2 things: that we can differentiate between a column and a wall by having the ratio of the depth to the width of the column. If the depth to the width of the column is going to go more than 4 times or more than 4, the depth to the width, then this is a wall. If it's 4 or less, that's going to be a column. And we say the column is going to take the loads from the different beams plus the self-weight. Now, what if we are having this particular, okay, what if we are having, let us say, okay, what about this column? This column is taking what loads? It is taking this particular beam load and this particular beam load, right? Now, of course, the slab will go to the beam will be transferring it to the column. So this particular column, if you say, is taking this particular beam, okay, it's taking this particular beam and this particular beam. Now, what about the column which is available at the bottom? Now, this column which is at the bottom is going to be taking this particular beam load, this particular beam load, as we said, the reaction of these 2 beams, plus it is going to take the column which is at the top of it. Okay. So once again, it depends whether we are talking only about a single column or we are talking about columns which is carrying different columns. Once again, this particular column is going to carry the reaction of the beams which are at the top. This particular column will first carry the beams and it will carry the column which is at the top. Okay. Okay. Are we clear about the methodology of calculating the loading on the column? Okay. Now going for slide number 3. We're going to slide number 3. Now concentrate on the unit of column because it's the most, or it's the easiest chapter where the students are increasing. I mean, where the students are getting most of the marks, and the concentration of your final exam is going to be mainly on the column of the, I mean, in the chapter of the column. Now, if you see here, we have different classification when it comes to a column. We have a braced column and we have an unbraced column. And once again, these information you have studied in Design of Structures 1. We are only recapping, so you will know whatever we are going to talk about whenever we are starting the actual design. Okay. Now, we have two scenarios. Scenario number 1 or scenario number A here, and then we have scenario number B here. Okay. And let us say that we have this particular column and this particular column. This is representing A scenario. This is representing B scenario. Okay. Now if you say in scenario number A, in scenario number A, there are no walls, there are no shear walls. Okay. In scenario number B, we have columns which are in blue, small x's, and then we have the red lines which are representing a wall. Okay. And we have two types of loading. We have loading number 1, whatever we call it as gravity loads. Okay. And then we have the other loads which are called to be lateral loading. And when we talk about gravity, we talk about death and we talk about life. Why we call them to be gravity? Because they go with the gravity. They go with the same direction of the gravity. Everything in terms of death and life, its own weight is going down only. Okay. Lateral loading, we are talking about wind and we are talking about earthquake or seismic. Okay. Now, in case number A, the columns are supposed to be taking both of the forces, both of the lateral and the gravity forces. Okay, because we don't have anything protecting my structure, or we don't have any element which is going to bear or to take the lateral loading. There are only columns, so these columns are supposed to be taking both the gravity loads and the lateral loading. Now, in case number or scenario number B, you will see that you have walls and you have columns. Okay? And in scenario number B, the columns are only designed or mainly designed to take the gravity loads only. Okay, while the shear wall are going to take mainly the lateral loading. Okay, so wind load, seismic load will be mainly resisted by the walls. Okay, will be mainly resisted by the walls. So scenario number A is called to be unbraced. My columns are unbraced against lateral loading. There is nothing protecting them from lateral loading. Case number B, it is called to be braced because we have other elements which are taking care of the lateral loading. Okay, so once again, scenario number 1 is called unbraced. Okay, why? We don't have any bracing, any kind of protection for our columns from any other element to take the lateral loading. So the column is forced to take the horizontal loading or the lateral loading. Scenario number B, we have shear walls available. Okay, so these shear walls or core walls are going to be taking mainly the lateral loading. That's the main reason why if we go more stories, okay, if we go more stories or more in height, 3 stories and above, you will see that always you would require to have a lift. Now the lift is structurally called as a core wall, as whatever we have taken in the drawings and plans earlier. Okay, we call it as a core wall. So you will see that the core wall is going to be present whenever you are going to go higher in terms of height. And whenever you are going to go higher in terms of depth, I mean in terms of height, the effect of wind and effect of seismic is going to be more. So now you will see that your core wall is not only, your lift is not only made for the purpose of going from a story to a story. but its main purpose when it comes to structural purposes, it is going to take the lateral loading. Okay. So this is an explanation of braced and unbraced. Braced means it is already protected against lateral loading. Other elements are going to take that particular loading, which are the shear walls here. Okay. And unbraced means the column is going to be taking both lateral and gravity loading. The picture here represents a structure which is having columns and shear walls, and you can see that the shear walls are going to be taking the lateral loading. They will take as well vertical loading, but mainly they are there to take the lateral loading. Okay, so that's the first classification. We should know what's the meaning of braced, what's the meaning of unbraced, and according to your plan, you should be able to figure out whether this column should be designed as braced or unbraced. The second classification we should know about is whatever we call short or cylinder. And once again, this is something that you have studied in your design of structures 1, design of structures 2. There is some kind of classification in which you will say that this particular element is a short element, or this particular element is considered as a cylinder element. Okay, and the BS code has specified it by saying that you have a ratio of LEX over H and LEY over B. Okay, LEX over H and LEY over B. Now we have learned that we have B. This is the width. The depth is normally called as D or is called as H when it comes to the column. So H is referring to the depth of the column. B is referred to the width of the column. L is referring to the length. Okay, L is referring to the length. So we have 3 dimensions for the column. We have length, we have depth, and we have width. Width is referred as B. Depth in some sources are referred as D capital, or here by the BS code is referred as an H. Length is referred as L. Okay, so we already know what's our H and what's our B. Now we need to go and check the meaning of LEX and LEY. Okay, LEX and LEY. Now let us say that this is my column. Okay, and I told you that the height of the column is 3.5 meters. The height of the column is 3.5 meters. Now the first thing that you should know that the column is measured always from the floor, from the top of the floor to the top of the other floor. Okay, the column is measured always from the top of the floor to the other top of the floor. Okay, it's not from the center of the floor to the center of the floor, or from the bottom to the bottom. It is always from the top of the floor to the top of the upper floor. Okay, so this is going to be my 3.5 meters. If I want to go and draw the free body diagram or do the idealization for it, this is going to be my length of 3.5 meters. Okay, this can be either a fixed or it can be either a hinge, or it can be either a roller, or it can be a mixture of different types of supports. Okay, now the whole length is whatever we call it as L0. That's the basic length. Okay, Now, figuring out which type of supports can be done using the VS Code, and we are going to take it in the upcoming classes if there is a time for it. Okay. Now, taking into account the first case, let us take scenario number 1 or case number A. Case number A, rather than drawing it vertically, I'm going to draw it horizontally, so I can understand the behavior. Now, if this is joint A small and this is joint B small, do we have rotation or do we have deflection at point A? You will see at point A, because of the fixed support, we don't have any kind of slope or any kind of deflection, and you can see that the failure is going to be of this manner. Now, the distance from A to B is whatever is known as L0, or the clear height, which is 3.5 meter. The distance between the modes or the points of failure is whatever we call it as our effective length. Okay, so the effective length is the distance from the point of failure, the starting point of failure, till the other end of point of failure on the other side. Okay, this is what we call as effective length, and it varies from one column to another column depending on the supports. Okay. Now, how to find LE? LE is found by an equation which is beta multiplied by L0, which is normally going to be, or assumed in most of the cases, to be fixed from both sides. Okay, which is going to be 0.7. The factor is going to be 0.7 multiplied by whatever value of L0 is going to give you your effective length. Okay. So now we learned what is the meaning of L0. We have learned what's the meaning of LE. But in these two ratios, there is something called LEX and there is something called LEY. Okay, there is something called LEX and there is something called LEY. Well, let me try to open something, or just to try to illustrate it for you here. Okay, so I brought a column. An RC column, whatever is the size, it does not matter. Okay. So this is the first one, the first height, and this is the second height. And then I have drawn 1B from this point to this point. Okay, so this is going to be, this is the model that I have drawn for you. Okay, this is the model that I have drawn for you. Now you will see in this direction, if I look at my, okay, if I look to my column from this particular direction, if I look to the column in this particular direction, I'll see that my column has been divided into two parts. Okay, has been divided by a beam into two parts. So this is going to be a separate column, and this is going to be a separate column. Okay, these from this side, these two columns have been separated by a beam. So we have one dimension or one direction here. Okay, we have one direction here. Now what about the other direction? In this direction, do we have any beam cutting the column? You will see that in this direction, if we are looking to it from here, you will see that there is no beam cutting my column. So this side is going to be taken full from the top till the end. Okay. So once again, from this side, if I look to it from this side, you will see that we cannot take the whole element as a column. Why? Because it has been separated by a beam. So this column is going to be 3.5 meter itself. This is going to be 1.5 meter itself. Okay, 1.5 meter column, 3.5 meter column. Now in the other side, when I'm going to design this particular dimension, you will see that in this particular length, we don't have any beam cutting it. So the column here on this side should be taken as a full 3.5 plus 1.5, which is 5 meters. Now, if you don't want to do that, then you are going to supply another beam on the other side. Okay. Now what happens? You can see whether your beam is taken from this particular view or from the other view, you will see that your column has been cut into two different directions. Okay. That's why the code has specified for you LEX and LEY. You have two directions where you need to see your column. Okay. Now in this scenario, we have 1.5, the length of L0 X, and 1.5 is L0 Y for the bottom. For the top, L0 X is going to be 3.5 and L0 Y is going to be 3.5. Now, if this beam is not there, in one direction, L0 X is 1.5, L0 Y is L0 X is 1.5. Okay, and then the top L0 X is going to be 3.5. On the other side, which is L0 Y, it is going to be 5 meter, which is the whole thing, since we don't have a beam cutting it from the center. This is only an illustration of LEX and LEY. We are not going to go in depth or trying to check the values of LE or LEX or LEY, but the thing that you should know, the concept of LEX and LEY. Okay, so now we have learned what is the meaning of LEX and LEY. Okay, the code says for you, if this ratio of LEX over H or LEY over B is greater than 15, or let's say lesser than 15, the first scenario. If it's lesser than 15, both of the ratios are lesser than 15, then this column is going to be considered as short column. Okay, once again, if my LEX over H is lesser than 15, LEY over B lesser than 15, okay, then this column is considered to be short. Now, if your LEX, for example, over H is 20, LEY over B is, for example, 16, both ratios are more than 15, so this is going to be as cylinder. If I have LEX over H, okay, to equal to, for example, 17, LEY over B to equal to 12, you will see one of the ratios is equal to, one of the ratios is more than 15, one of the ratios is lesser than 15. Okay, this particular direction of the column should be designed as short because it's lesser than 15. This particular direction of the column should be designed as cylinder because it's more than 15. The classification of the column itself, if any of the ratios is more than 15 or both of them, then this column is considered as a cylinder column. Whether you will be designing both directions as cylinder, it depends on the ratio for that particular direction. Once again, if both ratios are less than 15, then it is going to be short. If any one of them is equal to 15 or more, by the way, equal is considered cylinder. Okay. If it's equal to or more than 15, both of them, then the column is cylinder and both directions should be designed as cylinder. Now, if one ratio is lesser than 15, one ratio is more than 15, the column is considered as cylinder. One side, wherever the ratio is more than 15, it should be designed as cylinder. That side only. The other side should be designed as short. Okay, so this is the classification in terms of short and cylinder. Okay. Now, from these two classification, why we have explained them, we explained them for a reason, that whatever we are going to design is going to be your short braced column. Okay, whatever we are going to design, or whatever the most available in real structure, is the braced short column. Okay, and everything that we are going to deal with in this particular course is only short braced column. We are not going to deal with end braced. We are not going to deal with cylinder case. Okay, the last classification is going to be related to the loading before we start the problems themselves. Now, if we go to the loading, we have brought three different types of columns. Okay, we have brought three different types of columns. Now, before going to these three different types of columns, let us say that I have this particular frame, and we have a loading here. Okay. Now you will see this particular beam is going to have an end moment here, and it is going to have an end moment here. What does this mean? It means that this particular beam is going to push my column by a certain value of moment. So if this is your 20, then this is going to be my 20 as well. Okay. Now this shouldn't go as 0 because it's a fixed support. Okay. If this is, for example, 30, then once again this goes as 30. Now both of the diagrams here are correct. This one is correct, this one is correct. Okay, we call this one single curvature, and we call this one as double curvature, depending on the value of loading for both of the columns, depending on the length of the column in both of the scenarios. Okay, if you have drawn this way or that way, both of them are correct since you don't have the loading. Okay, so once again, to clarify, this is my beam. This particular beam is like this now. My bending moment goes like this. Whatever value you are having here, it is going to be the value of the rotation of the column. So if this is 20, then this is the initial position of the column. This column is going to be pushed by a value of 20 on the right side. The same thing goes for the left side. Okay. Now what about if we have this case? This is my frame. Let us have it now. Inch. And I have told you that this is 4 meter. This is 4 meter. Loading is 20 kilonewton per meter. Now you will see here what happens. You will see here that this particular beam is going to be having this shape, and this beam, the other beam, is going to have this shape. This is going to produce a moment here, a moment here, a moment here, and a moment here. Okay, and let's say, for example, that this moment for each beam is 50. So we have 50 here, 50 here, 50 here, and 50 here, because the loading is the same and the length is the same. Now you will see for the left column is going to be pushed. Now it starts from 0 here because this is a hinge. Hinge does not have a moment. Okay, so it starts by a 0. This is the value of the moment for the column, which is 50. Okay, the same thing goes for the right column. It is going to be pushed by the value of 50. Now what about the column which is at the center? The column which is at the center is not going to move from its position. Why? Because the 50 will be cancelled with the 50. So this particular column does not have any rotation or does not have any bending. This is in terms of a 2D. Now in terms of a 3D, if we have one column here, this column is linked to a beam on this side and it's linked to another beam on the other side. Okay, for example. Now you will see this beam is going to generate one moment. The other beam is going to generate the other moment. Okay, so if this is my column, you will see that this column is going to be pushed to the left, and once again this column is going to be pushed to the back side. So it goes in two directions. So we have one value of moment of x and another value of moment of y. Okay, these are not in the same direction. So we have seen where columns are having no moment. We have seen columns where they are having only one side moment, and we have seen columns where they are having we are having two moments. Column without moment, column with one moment, column with two moments. Okay, which are explained here in a very short manner. Now you can see that this particular column is taking 4 beams. Okay, is taking 4 beams. So first thing, I will say that in terms of n, or whatever is my loading, this will carry reaction number 1 plus reaction number 2 plus reaction number 3 plus reaction number 4. What about this n2? This n2 will be carrying r1 plus r2 plus r3. What about n3? n3 is going to be carrying only, if this is beam 1, this is beam 2, this is beam 1, beam 2, and then beam 3. Here we have B1, B2, B3, and then B4. Here we are going to have it as R1 plus R2. Okay. Now, if the column is interior, let's just try to draw it here. If I have a column, this column is linked to 4 beams. These beams are carrying exactly, if they are carrying exactly the same, if they are carrying exactly the same loading, if they are having the same length, you will see that we are going to have one moment here, one moment on the other side, one moment from here, and then other moment from here. Okay, what will happen now? You will see that if they are having the same length and the same loading, you will see that this moment will be cancelled with this moment. This moment will be cancelled with this moment. So we ended up only having N1. Okay, we only ended up having N1. That's only if the length and the loading are the same. Okay, which will generate for you equal moments. If they are not equal, okay, so for example, if this is 20, this is 20, 20 and 20, they will cancel each other. So this particular column will not move from its position. Okay, it will stick at its position. Okay, now going for case number 2, or the edge scenario. Now for the edge scenario, what is the scenario? We have one column which is connected to 3 beams. Okay. Now, if we have a moment here, and then one moment on the other side, for example, if this was 20 and this is 20, you will see that this 20 and 20 will be cancelled with each other. And if this is, for example, 30, you will see that this particular column will be having n plus 1 moment. Okay, because the other moments are cancelled. Now, what about the third scenario? We are having only 2 beams. Okay, we are having 2 beams. Okay. Now you will see that there is a moment on this side and there is a moment on the other side. Now there is nothing to be cancelled with because these are acting on different platforms. Okay, one is in X, one is in Y itself. Okay. So now what do we have? We have N because there are reactions. We have MX and we have MY. Okay. Now if for example in second scenario, if this is the second scenario, this is the third scenario. Now if in the second scenario one was having a longer beam and the other side is a shorter beam, this is having 50 for example, and this is going to be having 20. Now 50 is more than 20, so this will be cancelled, but still you will be having a moment of 30. So in that scenario you will be designing it for MX and MY as well, because you still have moments on both sides. Okay, if they canceled with each other, I can cancel one moment. If they didn't cancel each other, then still you will be having 2 moments. Now when it comes to reality, okay, when it comes to reality, we don't have similar beams when it comes to structures, unless for example you are designing symmetrical shops or you are designing classrooms, okay, where you can counteract the moment or cancel the moment for the different sides. But in real buildings, you will have, you will see that the length of the beam is different from the length of the beam. You will see that the thickness of the slab is different, so the loading is going to be different. So normally, when it comes to real structures, we are going to have moments. Okay, since we don't have similar length and similar loads. Okay, so in short, we have 3 scenarios. Scenario number one, where we are only designing for loading. And if we are designing for loading, we call this one to be actually loaded. Second scenario, if we design for one moment, either mx, if mx is there, then my is 0. Or it is 0 and my. So one moment only, either x or y. Okay. So we have n, mx, and my. This is the general. So here we have n, 0, and then 0. Because mx is 0, my is 0. So here we call it as actually loaded and uniaxial bending. When I say actually loaded, means we are referring to n. Actually loaded means there is n. Uni means 1. Bending means moment. So we are talking about one n and one moment. Last is going to be n, mx, and my. Okay. N, mx, and my, moments in both directions. So we call this one actually loaded and biaxial bending. Actually loaded, we are referring to n. Bi means 2. Bending means moment. So we have 2 moments. Okay. Normally the interior, if we are having regular spans, regular loading, for the interior, the beams will cancel each other. So it's actually loaded. Okay. Edge columns, you will have 3 beams. Okay. And in that scenario, 2 beams will cancel each other if they are having similar length and similar loading. And then if it's a corner, you will be having only 2 beams, means 2 moments directions. Okay. And we are going to learn how to deal with each and every type. Now, actually loaded, you have taken it in design of structures 1, but we are going to take a recap of whatever you have taken over there. And the next class, we are going to take uniaxial and biaxial okay, which is biaxial case. Now, the last thing that we need to do is to start solving the problem. But before solving the problem, I want to highlight for you what is the moment of x and what is the moment of y. Okay, so let me try to open this illustration. Okay. Now you can see here we have different types of columns here. Okay, different types of columns. Now, for example, let us say that I want to take this particular column. Now you can see for this particular column, you will be having 3 beams. The beam number 1, beam number 2, and then beam number 3. You can see that one beam is longer than the other beam. Okay, you can see that one beam is longer than the other beam in this direction, in the direction of x. Okay, in the direction of x, you will see that one beam is bigger or longer than the other beam. Now, if I want to see, let me isolate them first. Okay, so this has been isolated. Okay, I'll just remove the shape of the column so you can see clearly. So we have one column which is carrying 3 beams. Okay, now if I want to see the moment, okay, if I want to see the moment, you will see for the column, when it comes to the column, okay, when it comes to the column, this is my column, you will see that we had the bending moment for the first beam, which is the longer beam, the bending moment for the shorter beam. Now you can see, of course, because of the length, the left side beam, which is the longer beam, is going to have more moment. It has more moment than the shorter beam. Now you can see that this is a top moment for the left side beam. This is the right side moment for the shorter beam. Okay. The difference between them, so for example, if this is 50, this is 30, the difference between them is 20. You can see that the left side column is stronger, or it's going to be having more moment than the other side. Okay, so they will not cancel each other. Still, there will be a value of moment. Okay, so this particular beam is going to push my column to the right side. Okay, that's why you are seeing it in this way. You are seeing that the column is having a moment on the right side, not the left side. Okay, so this is in terms of one direction. Okay, what about the other direction for the column? What about the other direction? The other direction is from here. Okay, now you can see this particular column has been only pushed because of this beam on the other direction. So this beam is going to push your column to the left side from whatever I'm saying. Okay. Now, if you want further to highlight it, you can see that we have moments in X and we have moments in Y. I can separate the column only, and you will see that you will be having two moments. Can you see that you have two direction moments here? One which is MX, another one which is MY, because of the movement of because of the bending moment caused of the beams. Now, what about, for example, what about taking this, let's say, okay, still it has some value of moment. Okay, let us take another one. This column. This column. Now this column is taking two beams only. Okay, so if we separate them once again, if we separate them, removing the section, you will see that we are going to have this particular beam is going to push my column. Okay, this particular beam is going to push my column on the left side. Okay, so you are saying that the column has been pushed to the left side. The same thing goes to the other direction. If I'm seeing it from here, you will see that because of this beam, it has been pushed here. If I want to visualize both, now you will see whenever I'm talking about the column, you will see that I have two moments. Okay, I have two moments because of the values of the bending moment of the beams. According to that, you should be designing your column. If your column is having only one moment, then it should be designed as axially loaded and by uniaxial bending. There is one moment only. If it's two moments, then we should design it as biaxial. If it's only no moment, we should be designing it as axially loaded. I hope the illustration has made it a bit clearer for you. Now, the first thing that we are going to solve, or the first problem that we are going to solve today, is going to be related to one of the three types. So we said either we're going to have n value only, or we have n and one side moment, either mx or my, or we have n plus mx plus my. Okay. Now, if we go and read our question, okay, if we read our question, the question says for us a short braced column. So they have specified from the beginning that the column that we are designing is a short braced column, has a grade of FCU 30 Newton per millimeter square, and Fy is equal to 460 Newton per millimeter square, is required to support an axial ultimate load. So they have given us the value of axial load, which we have referred from the beginning, that the axial load is equal to n. So we have ultimate axial load. Ultimate means it's already multiplied by a factor of safety. That's its ultimate. And the question says for us, this remain a suitable section for the column if the area of longitudinal steel, okay, ASC, area of steel in compression, is if the order of 3%, means it's equal to 3% of the gross sectional area of the column. So now what I have found first, I have found that this is the case of only n. There is no moment of x, there is no moment of y, because it has not been given in the question. So only now are you able to hear my voice now? Okay. So this is an actually loaded case because we have n, we don't have mx or my because it has not been mentioned. Okay. It has been given that ASC is equal to 3%. So this is the second given data, that my AS is equal to 3% of the column, area of column. Now, if you remember, the column is only having two materials or two elements. The column is only having concrete and steel. If my steel is representing 3% of the column, then my concrete is going to be representing how much? It is going to be representing the remaining area of the column, which is 97%. Once again, if my area of reinforcement is representing 3%, then the remaining will be represented by concrete. Okay. Now, we will go to our code and find out what is the methodology that we need to adopt in order for us to solve for this particular actually loaded case. So we are going to the code, we are going to the table of contents. In the table of contents, we are going to go for the columns. So we are having columns here. This is the equation that I have talked about. Okay, this is the equation that I have talked about, which is LE is equal to beta into L naught. These are the cases. One is representing fixed, second is representing a hinge, third is representing a ruler. And how we are going to take it next class, hopefully, if there is time. It says for you, for actually loaded column, and if we are having nominal eccentricity, then you can use this particular equation. Okay, you can use this particular equation. So we return back to our question, where n is equal to zero point 0.4 FCU area of concrete plus 0.8 FY area of steel. Now you can see whatever loading is going to be absorbed, or whatever loading can be taken by the column, should be equal, or it should be representing the equilibrium of whatever forces can be developed by the material. Okay. So the force which can be developed by the steel, we call it FSC. The force which can be developed by the concrete is called FCC. Concrete in compression, steel in compression, because the column is a compression element. Okay. And we have learned that stress is equal to force divided by area. So if we want to calculate our force, then it's the stress multiplied by an area. Now you can see the stress of concrete is represented by FCU. The stress of steel is represented by Fy. Area of concrete is represented, or A is represented by area of concrete for the concrete, and then ASC is representing the area of steel. 0.8 and 0.4, these are the ratios. Not the ratios, but these are the coefficients. If you remember, the maximum stress in case of concrete, it is 0.67 SU divided by gamma m. The same thing, maximum stress for steel is gamma m divided by 1.05. Okay, so different values are there, in which if you go for the derivation, this is the come up equation. If there is time for the next class, then I'll show you how this has been derived. Okay, now returning back to our problem, this value of n has been given as 2000. SCU has been given as 30. Area of concrete, we have said it's 97%. So it is 0.97 of area of column plus 0.8. So it's 0.8 multiplied by Fy, which has been given already in the problem for 460. Multiplied by area of steel, which is representing the 3%. So 0.03 area of column. We will end up having 2000 into 10 to the power of 3 is going to equal a certain value of area of column. Okay, which is okay, and the question asks for determining a suitable section of the column. Can you give me this value? Can you multiply 0.4 into 30 into 0.97? Okay, and add it with 0.8 into 460 into 0.03. Okay, so that's going to be 22.60. Now, if we want to find our area of the column, then my area of the column is going to be 2000 into 10 to the power of 3 divided by 22.60. Can you give me this value? How much is this value? Okay, so we can say 88184. Areas are always without decimals. Okay, so 88,184. You will always round up or make it as a whole number without decimals. So 88,184. Now this is the area, but I need to get my suitable section. When I talk about section, I talk about the dimensions. it's square, then side. If it's rectangle, then it is going to be width and depth. If it is circular, then diameter. Okay. Now the question didn't specify for us the type of section, so you can choose any type of a section. But just for the sake of illustration, I'm going to try to have the three different types. So we have 88,184 millimeter square. Now, if we are having the first scenario to be a square, if this is going to be a square column, now for my case of square, we are going to have B and B. So my area is equal to B square. My B can be calculated as the under root of area, which is going to be the under root of 88,184. Can you give me this value? So this is 296.96. We cannot have this as my width. So what we are going to say? We are going to say that we are going to adopt 300 into 300. Okay, so my section in case of a square, we cannot have 296. I have explained for you. Okay, so it is 300 into 300. Now, what if we are having the second scenario, which is circular? Now, if it's a circle, then you will be having a diameter, right? My area is by d square over 4, where my d is going to be cross multiplication 4a divided by, and the square will go for under root. So we are talking about d equals to 4 times of 1184. Oh, sorry. 88184 divided by. Can you give me this value of diameter? Okay, so 335.08 mm. So what I'm going to say? I'm going to say adopt C, which is column, of diameter 340 mm. Okay, so I have given you square and circular. Last option is going to be rectangular. Once again, if this question comes in your examination, then you need to solve only for one of them. And the easiest is always going to be the square. Now I'm just illustrating for you the point if it has been asked to be a circular or it has been asked to be a rectangle. So if it's a rectangular, for a rectangular we are having B into depth. Now you will see, for me, there is only one equation, which is B into width into depth. I have one equation, but there are two unknowns, so I cannot calculate B into D unless I have another thing to help me. Now, one thing to help us that normally we use block sizes of 200. It means that normally my beams are 200, and normally my width of the column is kept to be 200, so it cannot go outside, or it shouldn't go outside the wall. Okay, if your width is more than 200, then you will see that your column is going outside the wall, because my width of the wall is 200. The width of the block is 200, means the width of the wall is 200. So now to sort out this thing, normally we keep our width to be 200. So we can say same as the width of wall. Now I can say that my area is equal to depth multiplied by 200. Okay, my depth is going to equal to area divided by 200. My area is 88184 divided by 200. Okay, can you give me this value? 441. So we are going to say that we are going to adopt 202, 450, a column of 202, 450. Doing that, we have finished one question in the column. Once again, columns are the easiest chapter among the chapters. The problems which are there in the columns normally does not take a lot of time. So concentrate a lot in the chapter of the column for your final examination. Okay. Next class, there is a problem of actually loaded as well, but I'll keep it. First, I'll cover uni-axial and bi-axial. And since your final examination is little bit, let's say little bit near to the end of the examination, then I'll be making later on revision classes for you, wherever you have a doubt for. Okay, so you can increase your marks. That's it for today's session. If you have any question, you are free to ask. If you don't have any question. Yeah, the block size is 200, so the wall size is 200. Always when you come to a real building, you will see that the columns normally are going to be 200. Unless there is a big restriction, for example, there is a huge load, 200 is not sufficient, you will go for 300. Okay, let me just show you an example. Hopefully we have something here. Okay, now you can see here, this is the schedule of column. The previous, let me just open it. This is whatever we call it as column layout. Okay, column layout. This is showing the position of columns. Okay, in your structure. And normally in the same sheet, we have the schedule. This because of the space limitation, we have kept it in another sheet. So you can see here that we are having, okay, we are keeping the width of the column normally is to be 200. Okay, 200 unless there is a restriction that the load is too much. You cannot go for something more. Now you can see here the designer, or as a designer, he has kept the width to be 250 to avoid the column from going more than 700 and then starting changing the column to the concept of being a wall rather than a column. Okay, so he has changed the width on this side. So once again, normally we start with 200 unless the load is too much, it cannot be handled, or the moment is very huge, then you can increase your moment. Now these are normally for architectural purposes. Okay, we have finished today's session. If you have any other questions,